quite well, and the sound is also very good. So. Okay, yes, but can you share your screen just to check if to see your presentation? If that's okay, we can start if you agree. Okay. We can see your slide, not in full mode, but yeah, we can see in full mode. Yes, everything is okay. So if you agree, we can start right now. It's okay?
I can start right now?
Yes, if you want.
Sure.
Let me introduce you, and then you can start your presentation, okay?
Sure.
Thank you. Okay, we'll start the second keynote speech at MCPR 2024. And it is my honor to present you Professor Ming Xu. I will read a short video of her. Professor Ming Xu is a fellow of IEEE and fellow of engineering in New Zealand. She is currently Professor of Artificial Intelligence, Deputy Head of School for Engineering and Computer Science, Deputy Director of Center for Data Science and Artificial Intelligence at Victoria University of Wellington in New Zealand. Her research focuses mainly on evolutionary computation and machine learning, such as evolutionary deep learning, feature selection, and image analysis, and the real-world applications in biology, healthcare, aquaculture, forests, and others. She has over 400 fully referred publications, outstanding, and leading several prestigious, many international conferences, such as General Chair of PRICAI 2025, Conference Chair of IEEE CC 2024, which will be in 1 week in Yokohama, Japan, and LGP 2024. She has also served as associate editor of several international journals, such as the IEEE Transactions on Evolutionary Computation, IEEE Transactions for Artificial Intelligence, IEEE Computational Intelligence Magazine, and ACM Transactions on Evolutionary Learning and Optimization. Thank you, Professor Ming Xu, for accepting this invitation. And you can start your presentation. The floor is yours. Thank you.
Great. Thanks for the nice introduction. Today is my great honor to give this keynote and to share some of the work on evolutionary and deep learning for image analysis. That's including the work we have been doing, as well as the work in the leading researchers in this field. So I'm from New Zealand, and this is where New Zealand is. It looks far away from many places, but it's actually not that far from Mexico. I was in Mexico for IEEE CEC in 2013. This conference is very close to the conference I'm chairing next week, so I unfortunately not be able to physically be there to give this talk. But I will hope we'll probably see you next week or sometime if you come to New Zealand. So I'm from Victoria University of Wellington, and for New Zealand or for Wellington, I'm not sure you know of the university, but I'm sure you probably heard of the movie Lord of the Rings and many other series of the movies which are taken in New Zealand, and many of the scenes are in the Wellington region. And for deep learning, looking at the program and the papers in this conference, I feel like I probably don't really need to introduce deep learning because I see many papers on the deep learning in this conference. But in general, I haven't seen an agreed or unified definition on what is deep learning. So we probably can just summarize. So basically, our understanding of the deep learning is more like learn meaningful representation of the data. Doesn't matter if it's image data, speech, vision, for language or even Tableau data or whatever data you have. Is to learn meaningful representation from the data and through a deep structure. And so via the nonlinear or layer by layer transformations. So we basically transform the data space in order to improve its representation of the data. That's very much what machine learning has been doing. However, if we add a deep, so it's through a deep structure, nonlinear transformation. So that is probably summarize whatever the deep learning models. So given this, that also means that deep learning somehow is not only deep neural networks. It could be many other different architecture or structures in the that can achieve what deep learning is supposed to achieve. And if we put in a big context, we deep whatever in if I'm looking at this, we're looking at AI as a big research, big field, and machine learning as a part of AI, and many of the machine learning algorithm, as long as they meet the what we call the characteristics of deep learning, so they can probably seen as a deep learning method. So that includes, as long as you have sufficient model complexity, you have a deep structure, you have learning meaningful representation, then that could be called a deep learning model. And then come out here, that means, well, not only neural network based, of course, the neural network based is somehow where the majority of the deep learning models are. So the most successful ones, the convolutional neural network, recurrent neural network, and again, other neural networks, of course, the transformers recently, even as well as enough, those they are very much neural network based. However, that's not only neural network based, right? There could be some other algorithm, for example, deep random forest and deep PCA models. And today, I would like to introduce some of more, which is evolutionary deep learning. Evolutionary deep learning is a kind of a new term. If you back to 2017, 2016, you probably don't have this term you can't find this term from Google. And now if you search for it, you see many papers or research related to evolutionary deep learning has been studied. And let's come back to we talk about the neural network-based models are most successful ones. So then why people start looking at the non-network-based deep models? I think that's come from mainly the current issues with the deep neural network-based deep learning models. Apparently, if you're looking at it, I'm sure most of us use quite a lot of ChatGPT, right? So that is one of the example of deep neural network-based models. They are increasingly complex and deep. So that's with ChatGPT 3, there's public available data showing that have 175 billion parameters. And you can imagine GPT-4 will only have a bit more rather than less, given the power it has. And also, Swift Transformer has even more, have 1.6 trillion parameters. I don't know how many of you have ever designed such a model. And for this conference, I guess the audience, and including myself, we're working on machine learning, we're working on evolutionary computation, we do a lot of algorithms. But myself, I haven't ever developed any of the models that having so many parameters. So within the parameters, you can imagine it's super computationally expensive to train them. So of course, almost all those models that need thousands of GPUs and millions, tens of millions of dollars, the training cost. And that's not talking about how with the data collecting data effort and lots of other effort behind. And another one, obviously, in AI, in machine learning, we talk about interpretable machine learning, explainable machine learning. So that's currently is a trend that is many of the methods, algorithm, or the tools we develop is a requirement by the government policies. So that means we have if we have a model with very deep structure with billion, hundreds of billions of parameters, I have no idea how we can interpret it. So that is basically impossible. So that is one critical point as well. Another thing is, for those design those models, we will need expertise in both the deep neural network domain as well as the problem domain. So the deep neural network domain that you can imagine, it's very hard for people who do not have a huge computation or let's say unlimited computing resources available. It's very hard for a single individual person to design a very large, deep, powerful models. So then, the models currently that are popular, and they often, for example, ChatGPT with how many people in OpenAI and design those models. It's often is a team of talent in machine learning with many years of experience, always have a PhD, of course, over dozens or even hundreds of those individuals that come up with design with a complex model. Let's not even talking about the problem domain. So, we have a lot of powerful pre-trained model available as well. But actually, if you really wanted to solve a real world problem, the real world I'm saying mainly is if you go to a factory, actually going to the factory physically, can be used, implemented, deployed there. That means that actually requires you to know about the problem domain you're solving. So there's many things that with assumption we have that's actually is not the case in the real world. So that means if we really wanted to put a deep learning model or AI models to the reality to benefit with our daily life, or tailor a tool for yourself, it's not that easy. And many of the, of course, for deep learning, another key important part is the architecture of the deep learning models. Many of them are actually manually designed for specific tasks, go through many rounds of trial and error to get it. For researchers like us, or for practitioners who do not have a huge team, who do not have unlimited computing resources, and who probably have a limited funding, I think what we really need to do is reduce the design, reduce the training, and I think we really need an automated design of the deep models. And that is partially what I want to focus on is the evolution deep learning. So that is one of the key is the kind of automated the whole process of deep learning model design. So come back if you don't know how many of you actually knows evolution computation. So if I'm looking at this, there is one way to categorize deep machine learning. So the 5 tribes. And, we are very familiar with, for example, support vectors and graphic models, the Bayesian models as well, probably also the logic symbolic models. So, and then the connects is this, that tribe is corresponding to the neural networks. In other words, the evolutionaries, that's corresponding to genetic algorithm or genetic programming. So genetic programming is one of the key algorithm in evolution computation that I want to focus on today. And so neural networks, I guess everybody is quite familiar with. And for evolution computation, so it's quite similar to neural networks. You have convolutional neural network, recurrent neural network, and many other different types of neural network. And for evolutionary computation, it actually also have different specific algorithm under evolution computation. So in general, it's more like a population-based algorithm inspired by biological evolution, Darwinian principle, or the fitness, survival fitness principle. So there could be in evolutionary algorithm or swarm intelligence, for example, particle swarm optimization, and genetic programming and genetic algorithms and other evolutionary multi-object optimization. So one of the big names in Mexico is Professor Carlos Coelho. He's doing a huge amount of contribution to the work of evolutionary multi-object optimization. So evolutionary computation in general can be, I would say, more broader area. So it not only can be used for machine learning, we call it evolutionary machine learning, it can also be used for optimization. A lot of work has been done on the optimization side, and recently has been a lot of work starting in the evolution machine learning side. So then, why for myself and for a large number of researchers who are interested in evolutionary machine learning, there are a few reasons, I think. So in general, the evolutionary computation methods it can be used for any aspect of machine learning. You want to tune parameters, you want to build a model structure, you want to do training, you want to do design, and that whole process can all be done automatically. That means you do not need to have domain knowledge. You do not need to assume any data distributions, differentiable or not differentiable. It doesn't require gradient information. It also can handle multiple objectives, as well as kind of constraints. So if we're doing that using evolutionary computation or evolutionary machine learning, well, essentially, if we want to build a model, we're mainly looking at model structure and model parameters. For many algorithms, especially for example, statistical method, they assuming model structure, then find the model coefficients. For evolutionary computation, that's not really the case. You can learn structures, you can learn the parameters or coefficients. You can also automatically learn both structures and parameters coefficients simultaneously. That's why it has been used for in many areas. And so evolutionary machine learning, we can then extend it to evolutionary deep learning. That means in the deep learning domain, it can also learn structures, coefficients, or learn both simultaneously. Here are some statistics that actually we collected from last year. And evolutionary deep learning, we have a survey that's published in ACM Computing Survey. We're looking at the evolutionary deep learning, but we're most looking at the EC and the deep learning together. Now, in many years ago, there are some EC algorithm and the deep learning. They might not actually evolutionary deep learning. They are just appear in the same paper in EC and deep learning. So in general, you can see it basically can be used for all the stages of a deep learning or machine learning domain, including features from obviously data for learning data from data preparation, that including pre-processing, including noise, removing noise, including imputation of missing values, to the model generation, and to the model deployment. It can be used in any stage using evolutionary computation. So that's a broad view of evolutionary deep learning. And if we're looking at, in general, event analysis, so currently evolutionary deep learning, probably the most widely used or most popular domain or application is evolutionary deep learning for image analysis. In image analysis, the most common one is probably the image classification. So that's if we divided the evolutionary deep learning for image analysis, so they actually occur then two branches. One is with neural network, deep neural net, one is without deep neural network. Without deep neural network, the key work at the moment is deep generative programming. And now let's first looking at evolution computation with deep neural networks. And there are many, of course, they have been used in many places, right? There's including that from early years, GoogleNet, ResNet, MobileNet, and transformers. So there has been various different ways to start the research using EC4 and deep neural network. So that's a neural network-based evolutionary deep learning. However, so you may think there's this evolution computation and deep learning and neural network is actually not a new area. I'm not sure how many of you have seen this paper from Professor Xin Yao in 1999. For this paper, it's a survey paper and looking at how evolution computation or evolutionary or evolving neural network, artificial neural networks. This paper that surveyed many papers in the literature, and it has a very nice graph, from 25 years ago. And if I can't bring this figure to summarize what the currently research has been doing, it can still cover. At that time, it's probably not the deep neural network, as mostly small artificial neural networks. So the key three areas in this domain summarized 25 years ago in the evolution of the architecture, evolution of learning rules, and the evolution of connection weights. We call it the learning of the weights. So from that time, and this structure, if we're looking at it now, it still applies. So majority of the research are still in these three categories. And the conclusion from 25 years ago, talking about the combination between the artificial neural networks and the evolution algorithm can lead to significantly better intelligent system than rely on only artificial neural network or EA alone. And this conclusion is still valid in most of the research as recent years. And some of the history, if you're looking at, it's actually a very interesting history from over the research actually from 1990s. And from 1990s, so the Darrell Whitley from the 1990 in GA for optimizing connections and connectivity. So for this research, if I am looking at the authors in this page, I found quite a few. Xin Yao, who wrote this paper, is a evolution computing pioneer award winner, and Darrell Whitley is another pioneer winner, and Risto McLean, he's another EC pioneer award winner. And there are other many or more, like Ken Stanley. He was in quite a few top AI groups in the big companies. So there's a lot. The people have been working on this area has made a huge contribution. And but that time before, let's say before 2017, 2016, a lot of work are mostly based on these small scale neural networks. There's not a lot of work in large scale, or we say deep neural networks. For the deep neural networks, for design of deep neural networks, only quite recently, there's not a lot of work in this domain, quite recently, when you evolving deep neural network. At that time, those are some survey papers that are looking at evolutionary design of neural networks. That's mainly the evolutionary design of the architecture of the neural network. The reason for not touching part of the connection weights is probably the number of weights is still too big to handle. So then the gradient descent method to search for the weights might be a better approach. And actually you can also see this method as a combination of evolution computation, neural networks, as well as the gradient method for the whole structure, whole process. And if we're looking at the neural architecture search itself, and I'm sure this is not a new term anymore, and the work done actually from 2016 from Google, from DeepMind and also Google Brain, I believe. So those two papers both the preprint in 2016 and the actual publication in 2017. So in this work, in those work, so most of the new architecture search method they using the reinforcement learning, and the ICML paper is using evolution computation. For then, these two methods in reinforcement learning evolution computation are the most popular methods in terms of new architecture design. And there were other methods, for example, random search, gradient-based or Bayesian optimization. There's a lot more research in recent years, and the new architecture search domain in general is very popular, and a huge number of papers published every year in this domain. And for the common design, I think still focus mostly on CNN and autoencoder, and also some Bayesian method. And the parameters normally optimize usually is the number of convolution layer, the number of pooling layer, number of fully connected layers. You can have the key hyperparameters that are needed to construct the model. They are mostly the ones that have been optimized by evolution computation. And to optimize this method and those hyperparameters, let's looking at, we're using evolution computation to optimize and looking at what are the key components or structures in the evolution computation. So there are, earlier I showed a diagram showing all the different types of evolution computation methods. But actually, if we summarize them, all of them can simplify it to this structure. So that means it's a population-based method. That means they have to initialize the population. Normally, we're doing a random initialization, so we randomly generate some solutions. And then you do evaluation, and you also do the generating new population, what we call updating, or you can think as a search process. And then if you wanted to use this method to solve any problems, it doesn't even have to be the new architecture search task. When you want to search for any algorithm in this case, basically what you need to do is to having the solutions or proposed ideas for these three aspects. So they're quite easy, but quite critical. So the key is a representation of the search space or encoding of the search space. For example, if you wanted to optimize some hyperparameters for some models, then the hyperparameter could be a vector. Okay, for the real value, the number of parameter you want to optimize equals to the dimensionality of the vector, and it could be a real value. So that vector is your representation, and the search space will be formed by this representation. Another one is the objective function, and in EC we often call it a fitness function for the Darwinist survival fitness. So every individual have a fitness. And then you can see this as an objective function, or you can see it as a loss function, say. So basically the key to evaluate how good the solutions are. And the next key is the search strategy. So what kind of a search strategy you are going to use? That including, how to updating the solution, there could be many different ways. So that is the key. So the search strategy is the key in terms of distinguish different types of evolution computation algorithms. For the representation, there can be many different representations. Commonly used could be a vector, could be a bi-level representation, could be a graph representation, could be a matrix representation. So the key idea here, so there is your representation will need to represent all the solutions you want to have, need to cover the optimal solution. But of course, we don't know. For example, we don't know how many layers of the deep neural network is optimal for a given task. So that's why because we don't know, and then many of the papers, existing work are actually using a variable representation. So that means it can represent any length or any depth of the architecture. That's actually involving two concepts. One is the architecture can be any depth. Another one is your encoding can be any depth. Some of them could use a fixed encoding. Say you have a fixed vector to represent the neural network of any depth. So that means you probably can, the easiest way is some of the dimensions are active, some are not active, then you can represent an architecture of different depths. So that encoding is fixed or variable, and the network could be fixed or variable. So there could be different ways to achieve this. If we're looking at one of the earlier work we were doing that, we're using this paper actually has a very large number of citations since published in 2020. So that is probably the highest citation in that year for atrophy transaction on evolution computation. I often like to introduce this work because it has a lot of considerations. Lots of considerations that are critical for a neural network to achieve good performance, but not a huge amount of computational cost. So the key idea of this paper, for example, the representation. This is actually we're looking at the work that done by DeepMind in 2016, 2017. And for the 2017 one, so the large scale evolution. So what they did is they use a fixed vector, but they use a variable length, but they can't use crossover in there, which is a critical search operator in genetic algorithm. And what we do is we're using a variable length representation for the reason that we don't know what is the maximum or optimal depth of the neural network. So you can see the representation can have different depths, different number of dimensions. And very simple, that's using C for convolutional, P for pooling, and F for fully connected. And then, of course, when you do population initialization, so each chromosome basically separated in two parts. One is the convolution layer, and the pooling layer can be any, can be any order, but the fully connected layer always to the end. And the length of each individual when they're generated can be randomly generated, and then you populate the vector to form a network. Another thing we did is for the fitness evaluation. For fitness evaluation is, for neural networks, normally if you have an architecture, you want to look in how good it is, you need to train the parameter in the architecture, right? And what we did is, you can imagine if for every single evaluation of the candidate architecture, if I do a full training of the weights, that's going to take you a huge amount of time, and also of the memory, of course. So what we did is we're using I think that this strategy has been borrowed by many researchers. So it's an early stopping. Early stopping is not new in machine learning, but what we did is, for example, I have an architecture already. I need to look in how good it is. I need to train the weights. Right? Normally, we train a large number of epochs on the training data. Here, assumption is we assume by a small number of epochs training, we should be able to tell the trends, right? How good it is. So what we need to see is which architecture is better than the other one. And then, we don't need to train for 200 epochs. We might be able to train just 5 epochs. And the better ones will continue better, of course. It will be better, even better. And the worst ones, we already might be able to tell which one would be better at the end. So as long as we have this prediction, we do need to train the 300 epochs. We only need to train 5 epochs, and we pick up the good ones. And we then, based on that, we do the next search. So by doing only limited small number of epochs, we hugely reduce the computation cost. But of course, at the end, you probably want to do a proper model. That means you optimize training of your. If we at the end we have, based on the 5 people, we have a good architecture, and we also want to use it for a test set, we will do a full training of the architecture. So every step of what we're doing is having some considerations, and it's actually not too complicated. The idea can be implemented in a quite easy way. And one of the work that the Google did in 2016, 2017 is that they didn't use a crossover operator. The key reason is because of variable length, and also probably because they have a lot of computational resources. They can do a lot of evaluations, which we don't have. So what we did introduce the crossover operator, that we basically do a union with collecting all the convolution layers, all the pooling layers, and all the fully connected layers. We only allow crossover of the same type of layers in the 2 individuals. So that turns out to work pretty well. And then for the other, we're using the binary Tolman selection. Now we considering the number of connections while we do the selection. That means that we prefer the one with a smaller number of connection or parameters. And we also have a weight initialization method for training the neural network. Now we're talking about we have only a very small number of training, very small number of epochs. But when we have actually for other to benefit the starting point, we just evolve the mean and standard deviation. So what is a good starting point for the weight in the neural network? And this algorithm seem to be work very well, and these many ideas can be used for not only convolutional neural network for other neural network as well. And we have the code publicly available. If you are interested, you can have a look. So we're talking about many different ways we're trying to reduce the computational cost. Then we're also looking at the work that Google has been doing in the recent years. So one of them, I don't know whether you have seen that, is a large-scale multitask learning. So that was developed by Jeff Dean, who is who is good at everything. So and then the whole thing he did is trying to using the goal is trying to develop an AI method that can solve tens of thousands of tasks simultaneously. On the different type of data achieved with a very high efficiency. I'm not sure about the efficiency, but it seems to be work very well. And the key idea, so you can have many different, as many tasks as you want, and using a complicated structure, and can solve all the tasks at the same time. The key idea of the work is actually using the evolutionary algorithm to automatically and dynamically adjust the exploration and exploitation to tune the hyperparameters. What they did is they actually do a very good job. They got the results, very good architectures on task, having 69 image classification tasks and have a good performance. But the only thing they didn't achieve, I think, is probably the computational efficiency. So they're kind of using 17,800 TPU hours. That's a huge amount of money. So I think this is probably, it has not been really widely used. However, it does bring us something, positive as well, right? That means that by having this, we can see there's a great potential for evolution computing algorithm to achieve these tasks. What we need to do is basically another problem for us to solve. And the problem of the task is apparently to reduce the computational cost. Maybe in a couple of years, I think in a couple of years, or probably in a very soon, there could be an algorithm to do smart enough to achieve what's the performance for the multitasking, but still having a low computational cost. This is all possible. And I see the potential, and if you're interested, I think this is a great area to work on. And we're talking about other parts as well, right? Not only we, evolve neural networks, there are other work that have been used to evolve the loss function. Loss function learning, that's the key part, right? If you have a loss function that give you a very smooth, nice landscape, it will be very easy to optimize. Then you think about how we're going to train the neural networks, so the ways, how much time we spend on. If you are guided by a really smooth, nice loss function, it will be much easier. So there's a lot of space for us to work on. So the next part we want to talk about is the evolutionary deep learning without neural networks. That means mostly it's deep generative programming. So very similarly, if you're not familiar with deep generative programming, the key idea is still, is a model. So if we do a classification task, so you input the image and you output the class label. And the model, instead of a network-based model, is a tree-based model. For the tree-based model, it's just very simple. But of course, this is a simple model. This is normally some years ago, before recent 5 years, there are a lot of GPU models are like this. Also, many using GPU for image classification is a machine learning algorithm. And now there's a lot of work in using GPU for evolutionary deep learning. That means, from the multi-layer perceptual to deep neural networks, from generative programming for deep generative programming, and that can be quite possible to develop deep models. So, a question you will easily ask would be, I already have neural networks, and why do I even bother to looking at another approach? Well, firstly, the research community need diversity. We're not only working on one specific algorithms, we're looking at all other promising alternatives. Another reason is with the tree-based structure, you can see it's much easier for us to explore the explainable decision-making process. One of the work that we did quite many years ago is we're using generative programming to do a task called facial expression classification. Right? One example here is the happy and the surprise face. Now you can see that for the GPU program of the models we have here, it's very simple. But it can achieve quite a lot. And so basically, if the input is an image, you can do regions detection, for the facial expression, the key area is probably your eyes, your mouth, right? You capture the key region, and then you do feature extraction from this region. The feature extraction process can also be representation learning. And then you do a feature selection, a feature construction, and then you do a classification. So the whole process can be done by this, 4-layer tree. 4-layer tree, that's very simple. And you can see which region are detected, which feature are extracted. So that gives you a huge potential for explainability. And of course, that is a simple one. We could have a multi-layer GP. That means the multi-layer GP, so from the input to the output, the classification. So the feature extraction process can be many, many, many layers. It is quite a flexible process. So if you can imagine that this process can go in many, many layers, as deep as needed. And there's a lot of further work in this domain. For example, if what we want to achieve is basically a flexible, a deep representation of the tree structure of the model. But of course, that's we do not always want to do deep models. What we want the simplest model to solve the task. However, if the task is super complicated, then we're looking for a deep model, right? So we do not always targeting to get a deep model. So GP provides us the flexibility. It can automatically determine how many layers you want, how complex your model needed to be. It can have complex functions. It can be having relatively simple functions. And then we're looking at some of the further work we did, is just we can define what we want in terms of, if you're giving an image, you wanted to see whether there's a cat or there's a dog. You do not really need looking too much over the background, right? Actually, many of the examples that showing the deep neural network is not doing what we wanted to do. It's many of the deep neural model looking at the background rather than the object itself. Then by doing so, if we're using a GP model, we can define, right? We allow it to do extract information from global, the whole image. We can also let the GP to do a local feature. That means I select the key region and then we decide. So the object detected could be a local region. So we do both global feature extraction and local feature extraction. Some of further work is we also can do, the flexible program structure. You learn different types of features from the image. What we have, you can see on the left-hand side, and that is we define the model structure. So we define the model structure. Here we define the input as the image, and we can have a filtering and pooling, and another combination of filtering or pooling. And we could also have feature extraction. And we have you can define your architecture as a fixed layers. So you have to have those layers, or you can define it having some flexible layers. So for example, with this structure, even with this structure defined, we still have a lot of flexibilities. If, say, exam program 1, so that is very likely that we're solving a task that's relatively simple. And we do not need a model like shown in example program 3. So because if the problem is simple, we want a simple model to solve it. And then when it's needed, when the problem is very complicated, it's almost impossible to using a very small tree or model to solve it. Then the algorithm will automatically learn a complex model, like from program 1 to program 3. So that is quite useful. So we do not need to the whole process can be automatically and very flexible. Okay, we're talking about how the whole process, and actually we can looking at how actually giving a model. For example, this model on this data set, it had 98% accuracy on both the training and test sets. And then we're looking at the image of 2 different classes, and then you can see that we can actually visualize step by step what the input data has been processed. It have some scaling. It selects some key region from the image, and it's doing a filtering, and you can still see the image, right? At some point, you will not be able to see the image, but you will be able to see what. So the very blur, very gray, not a face anymore, but the key part is still there. So that part can distinguish 2 different classes. You know exactly what the program is doing. Although it's not 100% explainable or interpretable, but there are some good ideas to show in that direction. And it doesn't have to be a complicated model, by the way. And we also can to visualize learn the features. If we're doing the feature learned the original data, and we're looking at how it can separate classes of different, the instance of different classes. You can see, for the flexible GP, the original data with a yellow and purple, you can see they can bio-separate it after you do the feature learning by flexible GP. So this is one idea showing the how GP being flexible and what kind of model is trying to generate. And how the model structure, it can be, we will invest in many more algorithm in this domain. So for example, we could even have we call it learn and evolving ensembles. So one of the reasons I think GP is being very useful is not only flexible in terms of the learning features, the filters and feature extraction layers, it's actually also quite flexible in terms of how you do classification. It could start from as simple as just a threshold. You output the GP value, compare with the threshold, let's say 0, then you decide which class it is. And that is for binary classification. It can be a bit more complex by having a model. For example, you can use a supervised machine, you can use a random forest as you doing the classification node at the top of the tree. It can be even more flexible, more complicated by having multiple different classifier, as what is shown here, the purple layer called classification layer. You can choose between supervised machines, random forest, or learn linear regression, or you can combine them as a whole as an ensemble. So that provides flexibility on the even classification process. So depends on what your problem need, right? It can be any way. So if your data shown to be really good by using supervised machine, your algorithm is supposed to automatically select them or not. If that's linear regression, your algorithm should automatically select this node. And if we're looking at classification accuracy, and actually doing a very good job. So even compare with not only the original or relatively simple algorithm, computer vision traditional algorithm, and even actually compare with the method we call EvoCNN. That's the method that evolve deep convolutional neural networks. So with a bit of design in the program structure, you can have different programs and for your different data sets. Now we can have ensemble of different classifiers. For example, random forest supervised machine, and it could be ensemble, right? You can do majority voting. You could have ensemble of ensembles. So ensemble means that your classifier selected could be ensembles. You ensemble the result of ensemble. So that means when you have a complicated task, you probably also have to have a complicated model. And then there are furthermore flexible layer representation. So that's some work. It can be very flexible. It depends on design. And some further work in the flexible GP multi-layer model representations. So you can have you can have all these different configurations in your algorithm. And some of the results that you can see, that is the performance in general are quite good if we compare with the different neural network-based model. And some further work in terms of further explanation of the result you can see is, again, originally we have the the face image to tell us step by step what the algorithm is doing, what the model is doing, and we can also visualize in terms of data, and then you could see from the bottom, and the very hard to separate instance of different classes. This is quite a large number of classes, right? And they can all mix together. And by doing each layer, by performing each data transformation in the GP model, you can separate more and more clearly. And then at the end, you can see it can perfectly separate it. To some extreme case, you can even looking at which dot it's not being classified very well, right? Then you can see by at what stage your algorithm cannot separate them. And then you can look at that instance. You can find the reasons why they are not separated well by this algorithm. But that can only achieve by you are able to visualize the process. And this is how the GP algorithm can do. And some more advanced work that we're using is the feature reuse, right? The previous GP work we did, there isn't a feature reuse process. So with basic layer by layer, just there's no what's it called skip connection like with neural network. But with the GP program, we actually can achieve that as well. And then, this some of the results here and actually showing quite promising as well. There's some examples you can see with the skip connection, we still be able to see what the algorithm is doing. And one of the recent work we did is we're trying to find the multi-skill features and for learning color features. Majority of the many existing work on GP is trying to turn the color image to a black, white, to a gray level image. And now one of recent work that we can directly handle the multi-skill color images. And if there are more work that we have this included in the book, and we also have the code available if you would like to work on it. Some of the key application domains, we're doing a lot in all the primary industries, climate change, environment. Of course, health and medical is one of the key regions as well. We're also doing quite a lot of not myself, but our center also doing quite a lot of policy ethics and with AI. And we have a data science and AI center. There's a lot of work covered by there. And I also finally would like to thank Anna for the invitation and also the MCPR 2024 team. And here are some of my students and my colleagues who contribute a lot to this work. And also, if you are interested, we have open positions for postdoc and PhD. And if you know anyone want to do an undergraduate, and we have undergraduate and postgraduate program from all the different lenses. Yes, feel free to contact us. Even if you would like to visit Wellington, visit our research center. We also having a conference in 2025. By end of 2025, there is a PRECI, which is have 22 years history for AI conference, and that I'll be the general chair for this conference that will be in Wellington. And finally, so I will be thanks for listening. I'll be more than happy to answer any questions if you have.
Thank you. Thank you, Professor Xu, for this very inspiring talk and showing a lot of the research you have been doing there in your university. So, it's time for questions. We have questions. Okay.
Thank you for your presentation. I think that very interviewers are very excited to have with us. I think that one of the main challenge in the NAS architecture search particularly is the computational cost. And mainly because we have a population-based approach where each individual has to be trained for a determined number of epochs, and also depends on the size of the data set that we are using and the resolution of all this. So have you considered, have you some experience with fitness predictors in order to achieve an efficient search process in order to reduce the computational cost? This is
this is a very good question. For myself, yes, we have developed some algorithm that we use we call there are different ways. One is to reduce the training data to a smaller size. The other one is very commonly used is using a surrogate model. So the surrogate model is so now we did quite a few works. One way you could do is you collect the information of the architecture that you invoked for the number layer, number parameter, and what called loss function you use. All those type of you can define many different properties you want to extract from the architecture. So you could do as what we have done is you could be a classification surrogate model. That means you predict. Normally, you can just compare with which algorithm, which architecture is better than the other. So that is quite easy way because in evolution computation for updating or for survival fitness, you do not need to know exactly what the accuracy can be. You just need to know which architecture is better than the other one. So that can be easily built doing a binary classification compared to architecture. So that work we have published in the actual transaction on neural network and learning system, TNLS. So that work is mainly for classify which architecture is better than the other. It's a super easy, super fast process. So you don't need to do full training. You could also do a way as you can do as a regression, right? Somehow that is probably a little bit more accurate on what you're doing. So that means that we also again collect information about the architecture and as well as collecting the data from your previous running of early generations. You have an architecture, you have data to describe your architecture, and then you have the corresponding fitness value or accuracy or whatever. And then by collecting this data, then you can actually build a regression model. Once you have an architecture, you predict which one at what level fitness, what fitness value it can have. So that was quite interesting that the majority of the work is actually doing in a regression way. But how you're going to, a lot of data actually is not continuous. How you build the regression model with a discrete or integer input value describing the architecture is not that easy. As well as you still need to, the other one of the way we do is we then kind of automatically updating the training data for the surrogate model. You need to have, again, we're talking about need sufficient training data to train a good model. And for surrogate model, it's the same. So you could doing during your whole evolution process, you could do some automatic adjusting of your surrogate data set, then adjust your surrogate model. Yeah, so there could be other ways. For example, you could do the one-shot learning, right? So you have you could also do we recently do quite some work on the without training free. So without training, that you basically learn your architecture in a way when you do the evaluation, you using training, so the training free approach. So I think the training free approach at the moment is quite a popular method. Whether it's this, some are entirely are really training free, some are not really training free, but so this is the way to do it. But this is a really good topic at the moment.
Thank you for this answer. Any other questions? There's another question.
Thank you very much, Benjo, for your presentation. It was a pleasure to listen in this speech because well, I seeing you or following you with with your research and using genetic programming to solve image classification. And something interesting that I've been seeing along the last years is that in the last works that you're presenting, you're including the image colors because the previous ones are not is not included the color for the problem. And my question is, at the time to use the image color, the features that are taken from the images is increased due to the different channels that that are included within the image. So there are some maybe technically to keep the computational cost in order to keep also the time, because I know that to evolve a lot of solution throughout several generations increase the team. Also the complexity tree along the evolutionary process increases. So there are several techniques. Have you tried several techniques in order to keep the performance and reduce at least to keep the same time during the evolutionary process?
For genetic programming based image analysis or event classification, yes, we have tried different approaches as well. And so, the common one is just surrogate model, and that's a lot. But I think so compared to what we do with deep neural networks and in generative programming, in the generative programming side, I think most of the work are rather on the data itself. So we have seen quite many work that, for example, if you train a neural network, you need a full training set, hundreds of thousands of images. But if you train a GP model, you probably do not need that many images. So reducing the training set is a very good way to reduce your computational cost. But then that does not mean that you keep the same training set from the beginning to the end, right? From the beginning, you could use a very small number of images for your inference evaluation. So that's quickly going to some high level information about the data. And I would say quite commonly that we do. If you really want to do a very high accuracy at the end, you could still using more data whenever needed. So that could be a very flexible dynamic process. So working on the data is quite a good way in terms of GP to reducing the computation cost.
Actually, I remember one question that I asked you. Have you ever tried some techniques at the upper layer before to the classifier, including something like PCA or LDA in order to decrease the features that you're taking from the images?
Have I using any PCAs to reduce the features? We haven't do that much. The main reason is normally we do not really need to do it. The reason is it also depends on which feature extraction method we are using, right? If we are using a feature extraction method that's actually generating a large number of features. That some of them are, for example, when we're using LBP to extract feature, there's a large number of features. We didn't really implement an operator to specifically to do the feature selection. And the reason is we can just enhance the GP tree itself do feature selection itself. So it's a kind of it's a built-in ability of GP to do the feature selection and the feature construction. I think I would, let's say, do not really need an algorithm to do that. The GP itself should be able to do it, but of course need some design of the tree structure itself.
Thank you.
Okay, thank you. Any other maybe final question? Okay.
I have one thing. Do you see any possibility that evolutionary computation is the way to find or decrease the high computational costs that machine learning techniques require right now? Do you think is the key to get a cheaper but very trustable artificial intelligence?
That's not sure I get the question because this mic doesn't seem to be quite clear to me when the voice comes in. Are you saying that do we see how evolutionary computation to reduce the computational cost in the deep learning domain? That's a super good question. I think that's the question I'm also looking for some answers as well. But I but I think the some good way to do is I think we really need to design smart algorithms rather than just exhaustive algorithms. I see deep learning domain and even some of the evolution computation research doing they just trying to spend running the algorithm for many iterations or epochs to achieve the good performance. But I think currently there's a huge and urgent need for reducing the computational cost. I think these three, the answer I could think about is we use it when we really needed to use it. Say if you have a simple problem, you don't really need to use deep learning. But if your problem is difficult for some part of your algorithm, you probably don't need to use a complicated evolution computation. Or you could use a simpler, smaller population size to reduce the computational cost. Another way I think, talking about the generative programming, actually I was talking with another, professor yesterday, is we're looking at the complex model. There's in terms of data transformation, there's always a way to learn a simple ones. And what we're looking at, we could using generative programming to allow it to learn a simplified version of the model. So quite a few years ago, we did using generative programming to learn what neural networks learn. For some tasks, it can derive a simpler model or equation to replace the original complicated ones. Yeah, I think there's a huge potential in this domain. Yeah.
Okay, thank you. This is a challenge
to deal with it. Well, okay. Thank you very much, Ming,
for your talk, for your time. We're grateful to have you here in Mexico, Mexico.
Yes. Yeah, we'll see you next week.
In person. Thank you very much.
Thank you. Thank you, everyone.
Thank you, and see you soon in Yokohama. Thank you. Thank you very much.
Okay, thank you. Bye.
Ok, terminamos día 2 en CPR. Mañana comenzamos a las 9 de la mañana con el 9 de la mañana. Mañana es día corto porque también el día un registro a Coatepec. Confiamos en que el agua no se haya ido, si sigue así el tiempo, parece ser que sí. Entonces, yo, pero mañana se